Hello everyone. What I'd like to do in this video is show you where all the 6 trig functions come from. What I mean is, how do the 6 trig functions fit into the unit circle? So, we already should know what sine and cosine mean on the unit circle. Sine is the height or the y-coordinate on the unit circle. Cosine is the x-coordinate or the width on the unit circle. Now, we also learned that that tangent is the same as sine over cosine. So, sine over cosine, a rise over a run, we can imagine tangent being the slope of this line as we rotate around the unit circle. It actually turns out that that's not traditionally how tangent was thought of, and that's not where its name comes from. That's a way that I like to think about tangent to help me quickly draw the graph of tangent or have me quickly see what tangent is, but it's actually different, and I'd like to show you that. Before I show you the 6 trig functions on the unit circle, what I'd like to talk about is the names of the trig functions. So notice that there's sine, and then there's cosine. There's tangent, and then there's cotangent. There's secant, and then there's cosecant. So where does this co come from? Okay, well, recall earlier in the quarter that we talked about the complement of an angle. Okay, so let's draw a triangle. So, if this is 90 degrees, we have a right triangle. Okay, let's just say that this is 30 degrees. So, since this is 30 degrees, and the sum of the angles of a triangle add to 180 degrees, if you haven't already watched my video about why that's true, make sure to check that out. But it turns out that the sum of the angles of a triangle always add to 180 degrees, or they always add to pi radians. So these two angles here must add to be 90 degrees. So if this is 30 degrees, this must be 60 degrees. We call these angles the complement angles. Any two angles that add to 90 degrees is what we'll call angles that are complement. So here we would say that 60 degrees is complement to 30 degrees. And vice versa. We would say that 30 degrees is complement to 60 degrees. Now, if we want to do this a little bit more, if we want to do this a little bit more generally, okay, so this here, let's call this angle here theta. Now, since the sum of the angles of a triangle add to 180 degrees, and 90 degrees is taken up in the right angle, that must mean that this angle and this angle must always add to 90 degrees. So let's call this angle here phi. So what I know is that theta plus phi must be equal to 90 degrees, or pi over 2 radians. So subtracting theta from both sides, phi must be the same thing as 90 degrees minus theta. So let's put that right here. So this will be 90 degrees minus theta. Okay, so let's take a look at the sides of this triangle. Okay, so let's call this length here, I guess this would be the opposite side, but let's call that y. This would be the adjacent side, let's call that x. This would be the hypotenuse, why not, let's just call it c. Okay, and let's remember, like, pretty much the definition, or pretty much the thing that this entire class rests on is SOHCAHTOA, or that, some old hippie caught another hippie tripping on acid. Okay, the class rests on this definition. Okay, so notice here, for example, that if I were to do the sine of theta, sine is opposite over hypotenuse, so that would be y over c. But notice also that if I were to calculate the cosine of the complement angle of 90 degrees minus theta, okay, that means we're standing here. We're standing here. Okay, I gotta kind of move my head down. Well, cosine is adjacent over hypotenuse. So if I'm standing right here, this would be my adjacent side, so that would be y over c. That would be y over c. Notice here that we have that the sine of theta is equivalent to the cosine of the complement angle, 90 degrees minus theta. So So you can think of what is cosine. Cosine, you can think of the we could say that cosine is complement to sine. And that's why it gets cosine. Okay, now it would also be true that the cosine of theta would be equal to the sine of 90 degrees minus theta, or pi over 2 minus theta if we're working in radians. Okay, now let's try the other ones. Or let's at least try one more. How about tangent of theta? Okay, so if we're standing right here, tangent is, I don't know, tripping on acid. Let's trip on acid. So tangent is opposite over tangent is opposite over adjacent. Tangent is y over x. But notice that cotangent of the complement angle, 90 degrees minus theta, that means, again, we're standing right here. Okay, cotangent is adjacent over opposite. So if we're standing here, this would be adjacent over opposite, y over x. So notice that tangent of theta is equivalent to the cotangent of the complement angle. So here we have that the tangent of theta is equal to the cotangent of the complement angle. Or we could think that cotangent is the complement of tangent. You know, complement in terms of angles, not like complement as in like, I don't know, hey, nice hat. Okay. So, and you can test the other ones, and it would also be true that cotangent of theta would be equal to the tangent of 90 degrees minus theta. Now you can check this for yourself, but it turns out that secant of theta is equivalent to the cosecant of the complement angle. And we'd have that cosecant of theta would be equal to the secant of the complement angle, 90 degrees minus theta. So these are some nice additional trig identities. These are nice to remember. Okay, so that's where the co comes from. You know, where does the name sine come from? Where does the name tangent come from? Where does the name secant come from? I know where tangent and secant come from. The name sine has a long history of where its name comes from, and it actually turns out when sine was first introduced, it didn't have the name sine, but it was translated, and somehow there was kind of some mistranslations, and somehow it ended up being sine. I don't really have a great understanding of where the name sine came from. I just kind of accept it, but the word tangent and secant, I'll talk about what those names mean. Okay, and let's see let's see these 6 trig functions on the unit circle. Okay, let's draw a unit circle. Let's draw a unit circle. Okay, so here is our unit circle. Okay, one thing that we'll always keep on our mind, SOHCAHTOA. Okay, so let's grab a point here on the unit circle. Okay, let's draw this line here. For right now, I'm going to make it a dashed line. Okay, this length right here, since it's a unit circle, we know that this length here will always be 1. And I hope it's clear. Got all my colors here, so I need red and green. Okay. I hope it's clear, what we've seen before, that we know that the height right here is sine of theta. So this length here is sine of theta. And I hope it's also clear to us, hopefully I've done it enough times, that this red length here, this is the cosine. The cosine of theta. Okay, so let's talk about tangent. Now again, tangent, since tangent is opposite over adjacent, tangent you could think is rise over run. That smells like slope, so you could imagine that tangent really is the slope of this line, but it actually has a different meaning in terms of length. So what I'm going to create here is something that's called a tangent line. A tangent line. So a tangent line is a line, the word tangent means to touch. So I'm going to make a line that just touches the unit circle. Okay, so I'm going to draw this length from here to here, from the point to the x-axis, this length right here. And I'm going to continue this line. I'm going to continue this line going up this way. Okay. Let's draw this one. Let's draw this one here in purple. Okay, we'll draw this one here in purple. So this would be a tangent line. It's a line that just touches the unit circle. Now notice with this line I've created, well, a good thing to think about is, well, I have this one right triangle that we've been paying mostly attention to, but I've actually created two other right triangles thinking about this line right here. Notice that since this line here is tangent, these lines here are perpendicular. So this must mean that this is a 90-degree angle, and this is also a 90-degree angle. So I have two other right triangles here. This is a right triangle, and this is also a right triangle. Okay, I forgot to write it, but this is the angle theta. Okay, so let's try to think about what these different lengths here are. For right now, let's just call this length here C. And I want to know what this length C is here. I want to know what the length C is. Well, notice if I take the appropriate ratio, what would be C divided by 1 if I want to know what cosine is? I'm sorry, if I want to know what C is, C divided by 1, I would like to get that ratio, C over 1, which is just C. Well, I'd have to be standing at theta, so let's see. I don't know, where are we? We'd have to be standing here. So if we're standing here, let's see, I would want C over 1. So if we're standing here, this would be opposite over adjacent. Opposite over adjacent, that must mean this length here must be the tangent of theta. Neato. This length here must be the tangent of theta. Interesting. So what's cool here is you could think about tangent as being the slope of this line right here, or you could think of it as the length of the line from the unit circle going all the way to the x-axis, and this line here has to be tangent to the curve. Tangent means just a touch. Okay, well, what about this purple length? What about this purple length? Okay, let's call this purple length, I don't know, how about we call it C? And let's try to see if we can think about what C must be. Okay, I need some more angles going on with this right triangle right here. Well, since I'm calling this here theta, and since this here must be 90 degrees, I know that this angle right here must be 90 degrees minus theta. Okay, so this is 90 degrees, this is 90 degrees minus theta. That must mean that this angle right here must also be theta. Sweet. Okay, we know that this length here is 1, and we'd like to know what C is. So we need to stand at the angle. So let's stand here. Bow, bow. Okay, so again, what we would like to get, if I want to know what this length C is, I'd like to get the ratio C over 1. C over 1. C over 1. Okay, if we're standing there, what sides would that be? Well, that's going to be, what is this? This is going to be adjacent over opposite. Adjacent over opposite. Adjacent over opposite. That's the reciprocal of tangent. That's the reciprocal of tangent. That's cotangent. Neato. So this length here is tangent. This length right here is cotangent. No way. No way. Awesome. Okay, so now we can see what tangent and cotangent are in terms of lengths on a unit circle. Okay, but there's other lengths. There's two other trig functions. Notice if we're thinking about all these right triangles, well, this specific right triangle right here, this is 1. We already know this length is sine, this length is cosine. This triangle right here, well, we know this length here is tangent, this length is 1. Well, what about this length? What about this length? What about this length? Orange. Orange. Hopefully that shows up. What about the length? What about the length from here? From here to here. From here to here. What would be this length? What would be this length? Okay. Well, let's think. Let's call this length for right now. Let's call this length here C. So if we're standing, we're our little stick figure standing. Okay, what would we want? We still want to get a c over 1. We'd still want to get a c over 1, which would just be c. Okay, so if we're standing here, we would need what? This would be hypotenuse over adjacent. Hypotenuse over adjacent. Hypotenuse over adjacent. That's the reciprocal of cosine. That's secant. That's secant of theta. So this length right here, this orange length, this is secant of theta. So that leaves us with one more. That leaves us with one more. And you're probably not surprised. Well, probably the other length here is going to be, what about the length here? We haven't figured out this length yet. Okay, let's call this length here c. You probably can guess what it has to be. It has to be the other one. We haven't done cosecant, but let's verify it. Okay, again, I would like to get the ratio of c over 1. I'd like to get the ratio of c over 1, so that'd be c. Well, if we're standing there, what would we need? We would need hypotenuse over opposite. Hypotenuse over opposite. Hypotenuse over opposite, that's the reciprocal of sine. That's the reciprocal of sine. That's cosecant. Cosecant of theta. So this length right here, this blue length, is the cosecant. This is the cosecant of theta. And those are the 6 trig functions on the unit circle. We can think about them as these lengths here. Okay, tangent, that means just to touch. Secant, the word secant means to cut. You could think of this line right here. This line right here kind of cuts the unit circle. And that's where it gets the name secant. Secant means to cut. Tangent means to just touch. Okay, you can actually think about these lengths here when we are when we're trying to sketch the 6 trig functions. Oh, before I do that, notice something. Okay, let's say we tried to find sine of theta, but we're standing here. What would be sine of theta? That would be opposite over hypotenuse. They're reciprocals of one another. Okay, we can use this to think about the graphs. Let's do a few of them. Let's think how we can think about this length here as being the graph of tangent. Okay, let's do it. So here is tan of theta, and here is theta. Okay, well, if we're thinking that we're at 0 degrees, this length here would be 0. So tangent of theta would be 0. This length here would be 0. Okay? Now, what happens as we rotate? Well, as we rotate, this length here is going to get super duper big. It's going to be really big. Now, essentially, when we are getting closer and closer to 90 degrees, or pi over 2 radians, when I have a, notice that I wouldn't even be touching the x-axis. So the length here is getting closer to infinity as the angle approaches 90 degrees. Or I'll graph this in degrees rather than radians. As we're rotating around, the length is getting bigger, and at 90 degrees, I don't actually have a line that touches from here to the x-axis. So it's undefined at 90 degrees. Now, if we rotate it a little bit more, we kind of move past this. Okay, this here would be tangent. It's from the point on the unit circle to the x-axis. Okay, so you could think here, well, if we're up here, we're gonna have a really long length, and as we move closer to 180 degrees, this length here is going to shrink. Now, in terms of length, you might think to yourself that it should be positive, that maybe the graph of tangent should look like this, but we know that tangent is the same as sine over cosine, and well, when we're over here, cosine is negative, so tangent must be negative. So when we're over here, we're just going to interpret this length as negative. It's going to start out super large, but super negative, and as we get closer to 180 degrees, it's going to be getting closer to 0. Going to be getting closer to 0, and then it's going to continue on from there. Okay. So let's do another one. Let's do one more. Let's do cotangent really quick. What about cotangent? What about cotangent? Here's my purple. Okay, well here's cotangent of theta, and here is theta. Okay, well if we're at 0, here's 0. Let's go to 90 degrees, and how about 180 degrees? Okay, well if we're here, there's not actually a line that's going to be able to go from a point on the unit circle to the y-axis if we're right here. So cotangent is undefined at 0 degrees. But as we rotate, this line is going to start out really, really long, and it's going to be getting closer to 0 as we get closer to 90 degrees. So it's going to start out super large, and then it's going to be shrinking. It's going to be getting closer to 0, to 0, to 0. And now in a similar fashion, when we're over here, okay, we're going to interpret this length here as negative because cotangent is the same as cosine over sine. Cosine is negative over here. So this length starts out, if we're over here, it's going to start out at 0, but then it's going to be getting really, 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 really large, infinitely large as we get closer to 180 degrees. So that's why cotangent has this shape. Let's do one more of them. Let's do one more. Let's do one more. I don't know. How about secant? How about secant? Let's do it in orange. Secant. Okay. So we draw slightly differently. Okay. Here's 1. Here's -1. Okay. Here's -1. Okay, so let's think about this length right here when we're at 0 degrees. Well, if we're at 0 degrees, this length here will be 1. It'll be 1. Now, as we rotate around, the length right here is going to be getting larger. It's going to be getting larger as we're getting closer to 90 degrees. And essentially, it's going to be getting infinitely longer. So this is going to be getting larger and larger and larger and larger and larger. Okay. Now when we're over here, secant would be from here to here. You can think of this as a negative length. Okay. In this case here, well, it's going to start out it's going to start out really large, and as we rotate, this length is going to be getting closer to. It's going to be shrinking. It's going to be getting closer to -1. So it's going to start out super negative, and it's going to be getting closer to -1. -1 when we get to what? 180 degrees. So it's going to start out super negative, and it's going to be getting closer to -1 when we get to 180 degrees. Okay, now if we go a little bit further, if we're over here, this would be tangent. Now I'm thinking about this length. As we're rotating around, well, we're going to go from -1, and then it's going to start getting bigger again. As we rotate, it's going to start getting bigger again. It's going to be starting to get closer to -infinity again. And this would be at what? This would be at what? 270 degrees. And it's going to continue on. And so this is why the graph of secant looks like it does. Go ahead, and as your own exercise, take a look at the graph of cosecant. What I'm going to do here is I'm actually going to switch to a Desmos animation, and I'm also going to link the Desmos animation in our week 4 folder, so you can play around with this on your own. Okay, we'll see you there. Hi everyone. So check out this animation. So here I have the unit circle, okay, and this length here is always going to be 1. Now what we saw on the board, is this green length here. This is sine. I kind of drew it in a different location, but this length from here to here should be cosine. We learned that this orange length here, I think that was secant. This blue length here was cosecant. We saw that this black length here is what was tangent, and this purple length was cotangent. I tried to color code the best I could. So let's take a look at these. We've already hopefully seen it with sine, so if you're using this on your own, I'm going to link this in our week 4 folder. So if you just click on the folder, you don't have to worry about what's inside of these folders. It's kind of what's going on in the background. But if you just click on the folder, notice that's turning the unit circle on and off. If I click on this here, it's going to tell you what sine is on the unit circle. So sine is that green length. Cosine would be this red length. and tangent would be that black length, and so on and so forth. So if you want to know what the graph of sine looks like, you can go ahead and click here and do the graph of sine. So I'm going to go back. This n is just the angle, so let's start at 0. And here we can see kind of how these lengths change as we rotate around the unit circle. So let's start at 0. We've already seen it for sine, but let's do it again. So sine is the green length. As if we graph it, we can see the graph of sine is recording this height here on the unit circle as we rotate around. So here's the graph of sine from the unit circle. Okay. Let's go back. Okay, and similarly, we also saw cosine. Cosine is this red length on the unit circle. Cosine is starting right here. This length, if I start at 0, it's recording a point right here at 1. And as we rotate around, it's recording that length here, this red length on the y-axis. So as we rotate around, we can see what the graph of cosine looks like from looking at this red length. Okay, let's look at tangent. Let's check out tangent. So let's graph tangent. So remember, tangent is the length of this line right here. Notice that this graph starts at 0, because this length here is 0 when I'm at an angle of 0. And as we rotate around, notice this black length here is getting larger, and that's why the graph is getting larger. So as we're going bigger and bigger and bigger and bigger, this tangent graph, it's getting huge. It's getting huge. That length is getting infinitely long. And now over here, we're thinking about this as a negative length. It's super negative, and now it's getting closer to 0, and this is just going to keep repeating itself if we're recording this black length on the unit circle. How cool is that? Okay. And similarly, see, we just did tangent. If we do the cotangent graph, okay, let's move this over a little bit. Let me zoom in. So remember, cotangent is this purple length here. Notice, can I go back? If I go back here, if I'm at 0, this length here is going to be essentially infinite. It's going to be undefined because I can't connect a line from here to the y-axis. If I move a little bit, I'll have like an infinite length, and that length is going to be getting closer to 0. And then, again, we're thinking about this length as negative. It's going to be getting really, 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 really negative. And this is a super positive length. It's appearing up here. We rotate around. We're going to get the cotangent graph. Kind of zoom in a little bit. Let's do that again. So looking at that purple length, it starts out really big. That length gets to 0. And we're considering this to be a negative length. It's getting larger and larger and larger, but really large negatively. Then we're going to have that positive length. Notice coming from the top, it's going to be getting closer to 0, so on and so forth. Beautiful. Okay, let's do secant. Okay. See this orange line here? If I click on and off, that orange line is going on and off. Okay, as I rotate around, I'm recording this length. Okay. Notice it starts at a length of 1. Oh, I should turn off my, oh, I should, oh, no, that's fine, never mind. I'm sorry, I was getting confused by this purple length here. We're paying attention to this orange length here. So this orange length, notice here, it initially starts at 1, and that orange length is getting larger. That orange length from here to here, it's getting larger. It's getting larger. Really big. And then now it's a super negative length. And it's going to be getting closer to, let's get the graph right here, let me move it. This length is getting closer to -1. Okay. And then it's just going to start getting more negative again. As it continues on, I'm going to zoom out. Push play. We're going to be getting the graph of secant. How cool is that? Okay, let's do the last one. Let's do cosecant. All right. Kind of zoom in a little bit. Definitely play around with this. When you get the chance. Okay, now as we rotate around, okay, remember that cosecant is this blue length right here. The blue length is super big, so that's why you can't see cosecant quite yet. But it's really big, and then this blue length right here as we rotate, when we get to 90 degrees, or this would be pi over 2 radians. Actually n is in radians. So notice when I'm at pi over 2 radians, or 90 degrees, look, this length here is 1. So, and now it's going to start getting bigger again. Now it's going to start getting bigger again. This length here is getting bigger again. As we rotate, we're going to get the graph. The graph of cosecant. How cool is this? How cool is this? Okay, so those are the 6 trig functions on the unit circle. I hope you enjoyed this video. Hope it kind of takes away some of the mystery of the trig functions. Well, make sure to play around with this when you get a chance. Okay, see you in the next video. Take care.